Right. A warm welcome to everyone joining us today. Today's CSC Development in Action webinar will be on developing a spaceborne atmospheric CO2 monitoring instrument. Today's webinar will be delivered by one of the three winners of the 2022 CSC Research Impact Award. The CSC Research Impact Awards celebrate the research and publication endeavors of Commonwealth scholars and alumni at the early and mid-career research stages. The annual awards are offered through two streams and promote the important research undertaken by doctoral Commonwealth scholars and alumni and its value to international development. I'd now like to introduce you to our webinar speaker, Commonwealth alumnus, Dr. Ikpaya David Ikpaya. Dr. Ikpaya won the 2022 CSC Research Impact Award, topical prize for his research around the clean energy area. And he will be presenting on this topic today. A brief introduction of our speaker. Dr. Ikpaya is the Deputy Director at the National Space Research and Development Agency, NASA, in Nigeria. He is a satellite engineer with vast experience of working in the space industry, specializing in spacecraft payload systems for Earth observations and remote sensing instruments. I'm pleased to inform you that Dr. Ikpaya is a 2017 Commonwealth Rutherford Fellow from Nigeria. He completed his postdoc in remote sensing instrumentation at the University of Surrey. And now, without any further ado, I would invite Dr. Ikpaya to introduce himself and also begin with the presentation. Over to you, Dr. Ikpaya.
Thank you very much, Eva. Thank you for that wonderful introduction. It's a pleasure to be here. Good morning, good afternoon, good evening, everyone who has joined us from wherever you are. Today's session, as Eva has already introduced, is on developing a spaceborne atmospheric CO2 monitoring instrument. And she already introduced me. My name is Ikpaya, David Ikpaya. We'll go through an introduction of myself, probably a little bit more in detail to what Eva has already said. And then we'll go into the paper. We'll discuss the paper which led to winning of this award, the development of Spatial Heterodyne Atmospheric Carbon Dioxide Spectrometer, which we call it SHACS for short. And in there, we'll discuss the overview of this research. We'll discuss the instrument concept and the design. We'll then move into the various stages of development of the instrument, and then present the test campaign and results. Also, we'll discuss the impact of this research and its contributions towards the SDGs. And finally, I'll share my Commonwealth scholarship experience. I hope you do have a good time today. As I've already introduced, I'm a Deputy Director at the National Space Research and Development Agency, NASA, Nigeria. I joined NASA after my graduation. I'm a graduate of physics from University of Calabar, Nigeria. I joined NASA in 2001. And then we went ahead to do with a training program called the Know-How Technology Transfer Training on the design, build, and launch of Nigeria's first satellite, NigeriaSat-1, at Surrey Satellite Technology Limited, SSTL UK. And after that, we did another training program, which was for the design, build, and launch of Nigeria's second satellite. This is the first satellite. And this is the second and the third one, the NigeriaSat-2 and NigeriaSat-X. And during that period, I had opportunity with when the team also went MSc program at University of Surrey. And then after that, I was sponsored by the agency NASDA to do my PhD still at University of Surrey, where the development of the SHACS instrument actually started, as you can see here. And then in 2017, I got the Rutherford Fellowship Award by Commonwealth Scholarship. And so that was 2018 to 2020, where we actually took this instrument development to where it is at the moment. And last year, and glory be to the topical prize from the Research Impact Award. Today we have a poll question just to kickstart the webinar, and which is just I think it's a fairly good simple question, which is, do you know what the CO2 monitoring satellite is? So let's see, take a few minutes to see what the answer is going to look like.
Okay, I think most of you have answered. I'll just give it another 5 or 6 seconds more before we end the poll, and I will share the results with you all.
Okay.
Okay, so I'm going to end the poll question now. I'm going to share the results. So most attendees today, 87%, have not heard or do not know what the monitoring satellite is.
Okay. Thank you very much, Eva, for that. And do our best to tell you what a CO2 monitoring satellite is. CO2 in the first place stands for carbon dioxide. And so a satellite basically is an instrument that is out there in space to be able to monitor or do Earth observation or do whatever we want it to do and give us feedback here on Earth. So it can be a remote sensing, can be Earth observation, can be communication, and so therefore CO2 satellites equally have a remote sensing instrument on board to be able to monitor atmospheric carbon dioxide and tell us the levels of CO2 across the globe. So that's what a satellite basically is, and that's what a CO2 monitoring satellite does. The results can help go a long way to solving most of the challenges we have. Thank you. So, an overview for this research, we'll discuss a bit more as we mention the concept of satellites so that we can really understand it a bit in detail. The aim of this research, which is why did we have to do this, is to find solutions to the effects of climate change. And by so doing, be able to understand the problem and be able to manage the problem. These are the basic things that led to this research. And how do we identify the problem? We will see in the next slide the solution of identification, and then the concept of identification, and so which basically there's an underlying and a problem based on studies which have shown that there is a difficulty in determining the CO2 flux extent in the tropics. That is not hard to find, because if you look at this picture, you see that all these dots, red dots in here, are CO2 monitoring networks, the terrestrial networks. However, if you look at closely along the tropical region, you will see that it's very sparse. And so the sparseness of these networks have not been able to let us know the extent of CO2 flux, which, if we know that very well, to go a long way to solve climate change issues. And so the solution is to have adequate space-based and terrestrial-based monitoring networks. In doing that, we need to first and foremost understand what a global carbon cycle is all about and how did we get here. The atmosphere, the lands, and the oceans have a fairly good balance, a good well mixed of atmospheric CO2 content. However, human activities such as fossil fuel emissions, cement production, land use change, you name it, industrialization have pumped in a lot of CO2 a lot of carbon into the atmosphere. And so this tends to upset the balance. Even though nature always works hard on resolving this, but studies have shown that there's always a budget imbalance, which cannot really be accounted for. If we can look at the areas where we have challenges in the sparseness of these networks, we can find a solution to this budget imbalance. And what do we call this budget imbalance? It's a measure of the mismatch between the estimated emissions and the estimated changes in lands, atmosphere, in oceans. Now, so if we can find this solution to budget imbalance, we can as well, be able to solve the global climate change crisis. Look at the graph, it just keeps going up. CO2 just keeps increasing year after year. Year after year, it's increasing. And as someone asked about the normalcy, what is the normal CO2 levels? And that varies. Are you talking about inside your house, if you're indoor, or are you talking about if you are outdoor? So this CO2 just keeps on increasing, thereby causing a global rise in temperature. And as we have the global rise in temperature, so that leads to global warming, and which leads to the climate change. And as of last year, you can see the graph here is shows about the CO2 levels got up to 418. You can see all the way from about 280 during the industrial era up to 418. It just keeps rising, and we have to know and bring that down to the barest minimum. And so the key roles here is being able to identify, and by identification being, we have to know where to look. And we've already found that out through studies that the terrestrial biosphere can be able to play a central role for us to know what to do as far as the global carbon cycle is involved, because the terrestrial biosphere holds the key to this budget imbalance. And we have to focus on the tropics, because that is where we have sparseness of networks, especially the equatorial region. And then how do we look? Space-based solutions and terrestrial-based networks can solve this problem. We can have final, spatial, and temporal resolution. Temporal resolution talks about the frequency of being able to get the result. How often are we going to get this data? How often are we going to get this result? And final spatial resolution meaning we're going to capture cloud-free data. And so constellation of satellites, CO2 monitoring satellites, is the solution to solving being able to do it at a very, very high frequency, such as what was proposed, like the A-train network shown in this diagram. And so being able to be able to develop an instrument of that magnitude entails being able to meet certain scientific requirements before we can talk about knowing the subtle changes of atmospheric CO2. One of the requirements is looking at CO2 in the weak region of CO2, which you're going to see in a model shortly, or in the 1.6 micron region, and in the strong CO2 band, which is the 2 micron region. And of course, your instrument must be able to incorporate the oxygen A band, which is basically to characterize the cloud effects. And instrument will be able to meet a very high spectral resolution at full width at half maximum, and then very high signal to noise ratio across the 1.6 micron region, 2 micron region, and of course the oxygen band, A band region. And then achieve very high measurement precision of less than 1% or better. And then we have high spatial resolution for clear sky soundings, as I mentioned. Now, meeting this requirement has led to very, very complex instruments, very expensive instruments, or very expensive satellites, if you want to call it that. And so government, industries just can only do one or two at a time. And that is not helping us. That's not helping the situation for us to have a constellation that we are into. The cost varies greatly between about $300 million to about $470 million. And so this is very high. And you won't take for granted because of the stringent requirements we have to meet scientifically. And so that led to us looking at the areas we are going to monitor, and which is the weak CO2 band and the strong CO2 band as presented in this model. The weak CO2 band is potentially free of water vapor. And so when we get a signals, we know that it is, we'll focus only on the region that do not have water vapor. And of course, that must meet cloud-free soundings. And however, the strong CO2 has a well mix of water vapor. But you need the two bands to be able to characterize your results, your actual result, what you have when you're out there flying in space. And of course, and they all have the oxygen A band to correct for cloud effects. And so to develop this, we already know the problem that we have at hand, which is the complexity of instruments and the cost implication of building such an instrument. So in this research, we had to look into a very cost-effective method to be able to do this. And we've gone through several options, and then we ended up with adapting the Spatial Heterodyne Spectroscopy technique, SHS for short. It is a very low-cost, compact, and robust solid-state instrument. It's been applied in the emission spectra widely. And so we now look into using it and have applied it in the absorption spectra. And it's very similar to what you can call a Fourier transform spectrometer, it's based on a Michelson interferometer. A Michelson interferometer is a typical Fourier transform spectrometer which has two mirrors. This is where we have gratings here, and these two gratings. In a Michelson interferometer, we actually have them as mirrors. So we have replaced those mirrors, and then one of the mirrors will be moving. So that introduces the complexity. We've eliminated all that complexity by having diffraction gratings instead of the moving mirrors. And so this instrument is solid, has reduced volume, we've reduced the size, reduced the volume, no complexity, no moving parts, and its mass is greatly reduced. Power requirement is reduced, very high light throughput, and very high spectral resolution. In so doing, we can then be able to manufacture these instruments with low-cost option. And this is a model of the terrestrial-based SHACS. A terrestrial-based SHACS, we've incorporated a scanning mirror, which you will soon know why we've incorporated this scanning mirror for the terrestrial base. So for in-situ-based networks, we've included this scanning mirror. Initially, this instrument was called the Compact Spatial Heterodyne Shortwave Infrared Spectrometer, or COMSWER. So, but as we continued further, we make the name a bit shorter and simpler by calling it SHACS. It has the two interferometer channels, or what you can simply say two basic cameras. It's more than a camera because it's a spectrometer, far higher than a camera. And then it also has a telescopic channel, a 3-mirror astigmatic mirror telescope. And so, as I said, for terrestrial base, we include the scanning mirror because the scanning mirror will be able to track the sun as the sun rises until the sun sets. without obstructing the instrument. However, for space-based monitoring, for space-based design, the scanning mirror is taken off, is removed, and only have a very compact and solid-state instrument. This design, which you've seen here, fits well into a microsatellite platform, such as the design I showed you about Nigeria Sat-1 in the first, in my introductory slides. So you can see that this design, but the 60 cm by 60 cm, fits well into a microsatellite structure. And in the development phases, we've gone through various stages from the lab demonstration, where we tested out a proof of concept. And so this was in the lab during my PhD. And the whole essence of doing this was just to get fringes, which we called an interferogram. That interferogram holds the entire solution to qualitative and quantitative results of your CO2 measurements, which you've captured. And so here in the lab, we used a halogen lamp as a light source and set up the instrument, and then we're able to get our results. As we proceeded further, this was sponsored by NASDA, Nigeria, my agency. And then during my postdoc, which was sponsored by Commonwealth, we had to test the instrument in a natural environment. However, the progress still had to be from the lab by channeling in reflected sunlight into the lab. The essence again is to check and be sure that what we got in the lab is the same what we're going to get. I'm using artificial light source, is the same we're going to get with the natural light source. And so we're using the sunlight. So we're able to still get our interferogram. And then we now put this instrument in a typical platform as it's going to be as a payload on board this SHACS satellite. And so this instrument, this size is constrained to being a 60 cm by 60 cm. And so it's fitted in well. So this is a way of saying, yes, our device is possible, we can do this. And then we can actually have sets of CO2 monitoring satellites, including the networks. So these have been the phases of the prototype that we've undergone. And so the next step was to then take this instrument out. And so I took this instrument, set it up, and then we started obtaining what we call the total column carbon dioxide measurement. You can see here, as I talked about the terrestrial based one. At this stage, we could not provide our ultrasound tracking instrument or platform, and so I had to use a car jack, and I had to lift this instrument up all the way as the sun rises all to its setting. And the Earth, of course, you know, is a very fast speed of about 463 meters per second. And so that means I had to keep tweaking the instrument to take measurements every 2 to 3 minutes per interval. And that's a very, very hard task. So that is why for the terrestrial-based hubs, our measurement networks across the tropics, for this instrument, we will require an ultrasound tracker, so that the instrument doesn't have to move, will stay in one place, and then the sun will just track, and then we get our total column CO2 measurements. And of course, to do this also requires a priori information. And so here we use handheld devices for pressure, temperature, and CO2, local CO2 measurements, so that we're able to quantify and validate what we have done. For space-based, we have the networks like the Mauna Loa network, which will serve as our terrestrial-based networks, or such as the observatory in Leicester. And of course, that has to be over clear skies devoid of clouds. And so from that, we then move over to the qualitative analysis to what we have. What we were seeking out for was to have an interferogram. This is typically interferogram. But from the instrument first, setting up a typical SHS instrument, you must have a zero path difference whereby all the lights constructively interfere. And so for you can get, because that holds the information. And so by applying a cross tilt to your gratings, you get your interferogram. And so this results of CO2 transmission spectrum was actually superimposed over a typical CO2, a modeled one, and it fitted perfectly. So for the open air results, you can even see that the interferogram is much, much more clearer. And since when I completed my research, which I had these things staying in the lab until when I went over to do my postdoc, the lab was still basically kept in place for me as if they knew I was going to come back. I don't know how they knew that. And so just getting in, I had to reuse basically everything that I had left behind to proceed for this next phase of instrument development. And you can see that the signal to noise ratio, which you're going to see in a minute, produce very, very good qualitative results of CO2 monitoring, a CO2 spectrum. And of course, this is from my handheld devices to tell you what it does. You actually need to know at the point of taking measurements, what was the actual situation before you started taking the measurement, so that you can always validate what you have in the retrieval process. And so we did what is called a signal to noise ratio analysis. And a signal to noise ratio is basically the end performance metric that determines the ability to collect spectra. And of course, a model showed that our concept is okay because the model showed we had more than 300 1, which is requirement says you have to get at least 300. It is about 700. And so for the halogen lamp at 1.6 micron center frequency, we're able to get 564, which is way above 300. And then under natural sunlight, it was greater than 900. And so this proves that this instrument is very not only robust, but very, very offers high performance. And the next thing was to, now they have the qualitative results, was to quantitatively tell us what CO2 it is, what we do with it. It's not going to make sense to ordinary the layman. What level of CO2 are we talking about? And so that is a quantitative analysis. And so we use the inverse method, the inverse model, following the works of Rogers and that of Hartmut, and a couple of other researchers to do the retrieval process. Each sounding for each measurement we did requires about 20 soundings, and each comprise about 30 frames of interferogram. You have to go through each of these frames to take the mean. And so for a typical sample, which we've seen here, you have about, about 600 samples to process. And you cannot do that manually. That had to go through an auto retrieval process for you to get each of the soundings for each of the measurements of CO2. And of course, we had a specification of meeting the spectral resolution of 0.27 per centimeter in terms of our resolution. Here we got 0.22, which is far better than what the scientific requirement stated. And though we did a trend analysis over what we've collected over the period of, this result is for May and June of 2019. For the remaining part of the summer period of 2019, it will be published separately. And so we performed a trend analysis. And for instance, this was that of June in the morning and then in the evening. in June 2019, and this is the result of the morning of May 2019. These results were taken from the instrument by performing total column CO2 measurement, which is the actual measurement required for this kind of research. And then we did a profile and just understand how CO2, which is actually well mixed in the atmosphere and varies greatly at towards the Earth's surface. And so this is why you always see this ramp for any kind of CO2 profile, because CO2 varies greatly at the Earth's surface. And of course, we limited that to 2 kilometers in terms of our pressure levels, because that is where the concentration is for the lower troposphere, where CO2, which is our focus for this research, was for the lower troposphere. And someone had asked in one of the questions about the precision, which we got for an instrument of this size. Normally, you see a traditional instrument spanning over more than 2.5 meters, but this instrument is just about 60 cm, and yet we will to get a precision of 1.27 parts per million. I mean, that is great. That's about 0.3% of measurement. And for this, just to make a bit of representation of what a space-based would be, space-based SHACS would be able to do. And our spatial resolution for clear sky soundings, as I've talked about before, is 118 meters. That's our resolution from a total swath of about 15 by 15 kilometers. And this instrument is not going to incorporate any scanning mirror. However, for mounting it on the ground, you can incorporate a scanning mirror and perform the original sounding. Our targeted altitude is about 700 kilometers. Rather than, I put it here that you have an option of putting a scanning mirror, but you don't really have to, because we can have what we call slew maneuvers of a satellite. And so the slew method eliminates the concept of the scanning mirror. And we are doing regional soundings. And so typically, as one asks, how frequent can we get this data? We can go into hourly period, 9-hourly period of 5 satellites on board. And all this is not, the cost of this is not even close to one current satellite that's being launched out there for CO2, for monitor CO2. What is the impact of this research? It cuts across various sectors. Of course, this provides a cutting-edge technology. It is innovative, and of course, it has a lot of spin-offs. And then it cuts across disciplines, environment, health and well-being, the academia, the industry, policy, management, technological advancement, and of course, socio-economic impact. For contributions to SDGs, it has addressed 13 UN Sustainable Development Goals. And specifically, direct is the goal number 13 for climate action. And of course, good health, good air quality, health. And so we have goal number 3. And then number 17 calls for partnerships. And then you can see that if we develop this instrument, and then we're going to, for the terrestrial networks, we're going to involve countries. We're going to involve countries within it, even want to look at only the equatorial region. We're going to involve the global world. Everybody's going to be part of this. And so that introduces partnerships and addresses goal number 17. Equally, the sparseness of the networks which we saw, as I showed you, we resolve this by reducing the inequalities. Why don't we have it across the equatorial region? Why don't you have it across the sub-Saharan Africa? This is where we have the abundance of the forest. And to look at the equatorial region up to the Amazon forest. And so we should have a sparse, we should cut across all this region. And so this also addresses inequality. And by developing this, you then see how goal number 1, no poverty reduction, comes in, because you're talking about innovative technology, reduces hunger, solves gender equality, everybody is involved. Even the management of the network, the CO2 monitoring hubs, affordable energy, clean energy, and people know that they are being monitored. Companies will know that, industries will know that they are being looked at, and there's knowing what they are doing, it's precisely to know where the emissions are from. This, and that leads to decent work and economic growth. Number 8, which ties also to number 9. This is an innovative infrastructure. And of course, 11, that produces sustainable cities. Of course, 12, responsible consumption and production. People will be able to know that they have effective ways of producing. Even if you want to go into energy research, they have to do it in a neater way that you're not polluting the environment because of the sanctions that will be involved. And of course, at the end, you have good life on land. And so my Commonwealth experience, which I'm going to share, I'll say thank you so much to Commonwealth for giving me a voice, even to present you this webinar, to talk to you about my work, and even we're going ahead to win the award. So this will give me a platform to do further research. And it also improved my research skills a lot, being able to analyze my data, write different programming skills, and be able to do data assimilation, add that to my work. And of course, access to VIPs, being able to meet VIPs, which you're going to see in the next slide. I got some pictures for that. And meet researchers, access to materials. And of course, my network has really greatly, during this course of this work, and connections really increased, and access to workshops and conferences. And you can see here opportunities as a Commonwealth scholar. It gave us, not sure whether Bola has attended this webinar. This is myself, this Bola, and then the rest were invited for, at arriving shortly, I think a month or 2 after doing our fellowship program, we were invited for a reception with the then Minister of State for Science, University Science and Research and Innovation. And that gave us opportunity to go to meet with VIPs. And you can see here Dr. Richard Middleton and Dr. Newman. So it gave us the opportunity. And then here is actually when Dr. Richard was discussing about my research and how it's space-based research was actually accepted into the program. And this gave us opportunities for workshops, and this is one of the workshops, interdisciplinary research at Leicester for only the Rutherford Fellows. And so it is giving me access to meet friends, colleagues, and expand my network, as you can see. So in conclusion, we've achieved very high precision measurement with these instruments to the tune of 0.3%. That's about 1.27 parts per million. So yes, that's very, very good for the size of these instruments. It's suitable. One instrument is suitable for both space-based and terrestrial-based monitoring. It's cost-effective solution, and in that we can have it in far less than $1 million. We're not talking about $467 million for just one instrument. We're talking about something far less, and we can have a whole setup, a whole constellation at a very, very cost-effective price. And of course, we build a set up CO2 monitoring networks across the tropics and have a constellation of satellites. And of course, as I've just said, we've focused primarily on sub-Saharan Africa and expand with partnerships with or other regions. It promotes bilateral relationship among countries in sub-Saharan Africa. I've talked about this, so this closes in on the inequality, which some people have asked in their questions. How can we make this available for developing countries? This is the essence of this research. You can support policymakers to ensure compliance from all countries to reduce carbon emissions. And so we'll be able to provide real-time data, not to wait and try to know who did what and who didn't do, who complied, who didn't comply. This can provide real-time data. And of course, it has addressed 13 UN Sustainable Development Goals. And this is me on a typical day going out there to do what I was sent to do, to do this research. And you can imagine in the summer period where you have the luxury of sitting out there enjoying the sun. And so it was really fun. And this would not have been possible without the Commonwealth opportunity. And this is my instrument, rolling it out and just getting it ready to start the work for the day. For future work, I intend to build and test the second channel and of course the oxygen airborne channel, funding permitting, and of course build and test the telescope module as well, and develop the ultrasound tracker for terrestrial-based monitoring. I would like to really thank my agency, NASDA Nigeria, for the opportunity that was given to actually start this research in the first place. And of course, through the Center of Satellite Technology Development, and part of NASDA. And then, University of Surrey for being a good host, and Surrey Space Center for always having me throughout the period of the research of undergoing this program. And of course, Commonwealth Scholarship Commission for such a great opportunity to get to this level. I also want to say a big thank you to Eva for really putting this together, for organizing and making sure that we can actually have today and discuss my work. And Davina for joining in, for your contributions throughout this period. And I'm especially grateful to Almighty God. Without him, God is trying to say, but yeah, I'm really grateful to God for making it that I was able to win the 2022 Research Impact Awards. Thank you, the topical prize. These are my references. Yep. Any questions? Any?
Thank you so much. Thank you, Dr. Ikpaya. I really enjoyed the webinar, and it was lovely seeing your the pictures that you put together of your experience whilst you were a Commonwealth Fellow. So it was really great, and I'm sure the scholars and alumni attending the webinar feel the same. It was great to know more about your winning research article, and also understanding your work and explaining what a carbon dioxide monitoring instrument is and its usefulness in tracking climate change, and how this also contributes to achieving UN Sustainable Development Goals. So yeah, thank you so much from the entire CSC alumni team and the wider CSC community. In terms of the next awards, and this is for the scholars and alumni in attendance of this webinar, in terms of the next CSC Research Impact Awards, these will open in June 2023 to all current doctoral scholars and alumni with up to 10 years post thesis submission. So all those who are eligible to apply will receive an email notification about this award sometime around May or June. So do keep your eyes open for this information. I would now like to open the Q&A session. Dr. Ikpaya, if you're ready, and for all those who would like to send in your questions, we have around 10 minutes, 10 to 15 minutes for the session. So please send in your questions via the chat box. But I also appreciate everyone who have sent in their questions via the registration form. So I'm happy to address some of these or like pose some of these to our speaker today. So, Dr. Ikpaya, your first question, and this is a combination of a question that we received in the chat box and also in the registration form. So, the question is, what is the average cost of this CO2 monitoring instrument, and how accurate is this instrument?
Okay. The average cost of the CO2 monitoring instrument, it depends on which method you are going into to design. The traditional method, which is what we have there, for instance, the orbiting carbon observatory, the OCO1, which failed, and then the OCO2 and the OCO3, or you look at the GOSATs, that's the BICU satellites. The average cost is about, say, range OCO is $280 million. GOSAT is about $467 million. And so if you look at that and then compared to what we have, that is because of the design and the approach which they have undertaken, compared to something which is less than $1 million. So yes.
Thank you so much for sharing that information.
And the accuracy is actually very high. The existing ones are very, very high, and it's comparable. GOSAT was about 4 parts per million, and what we have produced here is about 1.27 parts per million, which is the range of the OCU, which is also about 1 parts per million. So by performance scale, our instrument matches very well with what is existing out there.
Great, thank you so much. Just a follow-up question to that. What measures are in place to ensure that countries are adopting and implementing that cost-effective and affordable means of monitoring atmospheric CO2 levels globally?
There are global climate actions in place to ensure that countries meet or comply with towards carbon neutrality. So such as the COP meetings, the Conference of Parties, whereby almost all countries have signed up to COP. And so these are one of the measures. However, it's not setting this up that is the issue, or it's not a country signing up that is the issue, but being able to comply. And how do you monitor for compliance? So this is the main problem. This is the target, and this is where we come in to solve. Because of the cost of producing just one, which is very high, which is very complex. And so if we come in and fill in the gap by having a constellation whereby everybody's checked on an hourly basis, and so the being able to comply makes it easier. Thank you.
Thank you so much for that comprehensive response. The next question is around policy. Can the device help in implementing policies to curb the menaces that destroy the environment, such as illegal mining and so on?
Yes, and just to add, that is similar to what I've just mentioned. Not only can our instruments monitor atmospheric carbon dioxide, the instrument can be scaled up to monitor methane as well. All we need to do is just to change our literal frequency by just tilting off the gratings and start monitoring methane. And so we can have a network of satellites, and if not one set monitoring methane and one set monitoring atmospheric CO2. And so at these sites, the level of combustion, mining sites, that what's being thrown up into the atmosphere can always be monitored, can always be tracked. And so that can lead to knowing what is going on at those particular sites. But to do that is even easier, if you say it here, because of what I do, satellite technology. You can go into visible spectrum. The visible spectrum, we just on any cameras, you can be able to track and do and monitor mining sites, effectively. And one of the spin-offs of this is the region which we are using, which is the short infrared region. Looking at that spectrum, we'll be able to narrow it down and focus primarily on, if mining sites were our targets, we just focus only on mining sites. Thank you.
Thank you so much. There are a couple of questions coming in the chat box, and great positive responses to your presentation and your research. But before that, I'd still like to ask you one more question from the registration list. Does the equipment only monitor carbon dioxide, or does it also measure other harmful gases within the Earth's atmosphere? And also a second question, how is the data shared, and is it going to be publicly available globally?
Okay, thank you very much for this question, which I've just answered earlier, that the instruments can monitor not only, the instrument is scalable. It can monitor not only atmospheric carbon dioxide, it can also monitor methane. And so that is one. These are the two major gases that we can look into with this instrument. And so the second question was on Eva, can you just repeat the second question?
Yes, sorry. The second question is the data that you received through this.
Hello, Eva.
Hi, can you hear me, Dr.
Okay.
Ikpaya? Can you hear me?
Okay, yeah.
Yes, so the second question is, how is the data?
Yes, I can hear you.
The second question is, how is the data shared?
Yes, I can hear you.
Will your data be shared publicly?
Can you hear me?
I can.
Okay, good.
The question is,
yes,
how
the data can be shared, will be shared publicly for scientific users. For those, yes, the data can be shared publicly with scientific users and researchers. The essence of doing this is for the scientific community. And so without us sharing the data, it doesn't meet our end goals, and the information does not get to the right people. And so the data from these sets of measurements will get to scientific users and the scientific community. So the answer is yes, this data will be shared publicly. And you can also log in and have access to, we make it into an app whereby real-time apps, you can log into the network and then be able to know what is going on around your locality, where you are, wherever in the world.
Thank you so much. I hope I'm audible. The next question is, does NASA get any support from high-income countries when it comes to conducting research?
It's difficult to say that, but I want to tell you primarily NASA NASA has a pool of researchers from all areas of discipline, all areas of research. There are more than, I'll say, 200 PhD holders in NASA, and more than 1,000 master's degree holders. So it's at a pool of researchers. So that's just what I can tell you about NASA. So yep. Hello.
That's a great response, and it just shows the impact that it's having through the scholars and the researchers at NASA. The next question is, how vast can the instrument measure CO2 emissions?
How best can the instrument measure CO2 emissions?
How vast?
It can do it to the scale of 0.3. How? That's how best can we do this? We can do this to the scale of 0.3%, which is very high. The instrument is very, very high performance. It's a very, very high performance instrument. And so we can measure CO2 to that precision. And that meets our scientific requirements even better. That's what the set goals are.
Thank you so much, Dr. Ikpaya. I'm not sure if the next question is related to your current response, but the question is, what is the spatial resolution of this instrument?
That's about, it's 118 meters. And that resolution is enough for us to be able to avoid clouds and have measurements devoid of clouds and aerosols.
Great.
That's why we aimed at that high resolution, 118 meters.
Great. Thank you so much for that question in the chat box, and I hope that that answers your query, Aarti. I still have one more question in the chat box. The question is, what action is taken based on high carbon dioxide level to safeguard the health of the public?
Basically, that's the essence of this research. The essence is to make sure that rather than seeing the graph as we saw the CO2 level graph to skip being on the rise, we can get to the point where that can start coming down. So far, it doesn't impact health. It just impacts the climate, thereby then inadvertently just then impacting health. And so whereby we can stabilize this and start making sure that the CO2 emission levels do not increase anymore, and that's checked, instead we can begin to see a decrease or a decline in the graph. That is where we can say, yes, we've gotten to safety limits.
Okay, and right on time with that question. Oh, we have one more question. Just one more question, Dr. Ikpaya. What was your greatest challenge in this research? And that's a very good question. What were your challenge while you were conducting this research?
Thank you so much for that question. I think let me just share briefly my story. Undertaking this research under the supervision of Professor Craig Underwood, Emeritus Professor at Surrey, and was actually initially it was a bit so challenging because I wasn't sure how the results is going to turn out. In fact, at some point, we're not looking at even getting something useful, because in every area that we looked at, it appeared the instruments just have to be large. All the designs that we tested to making sure that we can have a very small instrument. In fact, there is a prism which I designed, and it was named after me, called Ikpaya Prism, but it didn't do the work. It didn't meet what we were supposed to do. All areas we're looking at, just that if this have to meet this requirement, this stringent requirement, then the instruments have no choice but to be large. Until, just not giving up, just continuing and doing the things. So that was the bigger challenge, was to look in closely into other areas, what we can adapt and what we can use and what novelty we can add to be able to combat this challenge. And of course, funding. Funding for this research was also another constraint, major challenge. Because most of the things you want to look at, you want to buy a detector, even an in-gas detector. You're talking about in the tune a short-range infrared detector, not an in-gas one. You're talking in the tune of about $180,000. And so who is going to sponsor that for a PhD research? And so luckily for me, we had to devise a means whereby we can use very, very low-cost options to achieve the same results. And that's why we had to focus the research only at the 1.6 micron region, as you can see, because of the cost implication of going into the 2 micron region. So we had to limit it to that level and decide, okay, let's do this. If we finish this aspect and be able to get our quality interferograms, then we know that we've hit it exactly where it should be. And then the rest will just be as funding comes through. So one of the challenges was funding as well, apart from being able to know and getting the right novelty to do this task without making sure that making sure that it does not have any moving parts, which is also a constraint I have. Make sure that nothing is moving. That's the only way we can remove the complexity. And so removing that complexity, making sure that it is solid states, no moving parts, solved the problem. Thank you.
What a great response to end the Q&A session. Really great describing the challenges that you experienced while conducting your research, and I'm sure our scholars and alumni also have also faced or experienced challenges in their research. So great learning, great takeaway for them as well. As I've mentioned, if you are interested in getting in touch with Dr. Ikpaya, if you'd like to connect with Dr. Ikpaya to know more about his winning research article, to know more about his research, please send him an email. You can see the email address in the on the screen. Dr. Ikpaya is also available on LinkedIn. Please do connect with Dr. David Ikpaya on LinkedIn as well. He'd be very happy to answer any queries you may have about the research or just a general connection. So thank you so much, Dr. Ikpaya, for your brilliant presentation. And thank you so much to all our scholars and alumni who attended the webinar today. Before we end the webinar, do you have any final words before we end the session?
I just want to thank everyone for finding time to participate in today's session. I'm utmost grateful for your time. Thank you very much. I really appreciate it. And to other awardees for the 2022, thank you so much. I also enjoyed your presentation in the last webinar. And to thank Commonwealth, thank you very much, the alumni team, for all your hard work you've put in for this to be a success. And trying to say thank you, NASDA, for this opportunity. And appreciate, thank God as well for making sure this is a success. Thank you so much. I really appreciate you all.